coming back from the break, but we have 3 talks this morning, so let's just move on. Our second talk is Paul Seidel, who is going to tell us about the quantum connection and small P reduction.
Okay, can you hear me? On. Okay, thank you very much for inviting me. I feel that this screen is a lot bigger than the mathematics that I put on it. So the result of this talk are essentially elementary, which means that, with one exception, elementary meaning that the techniques used are not really more complicated than the definition of the quantum connection. So that's the simplest level at which you can geometrically talk about the quantum connection. In spite of that, it is quite possible that you'll find it completely incomprehensible, which is due to my famous skills in explaining stuff. So the first part of the talk is joint results with Dan Kumaleano, should be a joint paper. And the second part is, I think, myself, but it is all very much motivated and inspired by the results of Zihong Chen, who, still is my PhD student, who's about to graduate. And if you're interested in flipping left and right in those slides, they're actually up on my homepage, so you can download them. Okay, but before I start with the quantum connection, I want to do some motivation of some more classical thing, which is vaguely related to mirror symmetry, which is singularity theory. So I take a polynomial with an isolated critical point, say the origin, and the basic algebraic invariant is the Milnor ring. So you take the ring of, say, formal power series, and you divide by the Jacobian ideal of generated by all derivatives. This, because the singularity is isolated, this is a finite dimensional complex vector space, and the dimension of that is the Milnor number mu. There we go. Okay. Now, this vector space, this ideal contains all polynomials that vanish to sufficiently high order in zero. So in particular, there's some power of the original function which lies in the Jacobian ideal, and it is a non-trivial theorem that in fact the power that lies in the Jacobian ideal is just determined by the number of variables. So the n power always lies in the Jacobian ideal. Of course, it could be that a lesser power lies in the Jacobian ideal. The simplest case would be that f itself lies in the Jacobian ideal. Now, if you suppose that f is homogeneous, then just by differentiating the homogeneity condition, you will write f as a combination of the coordinates and the derivatives. And that's also true in the weighted homogeneous case. So if it's weighted homogeneous, then f lies in the Jacobian ideal. And it is a theorem of Lie that the converse also holds. If this f lies in the Jacobian ideal, then the singularity is equivalent in terms of change of variables to a weighted homogeneous. So this is all purely algebra. It's done in terms of polynomials, power series. From a topological point of view, the basic thing is the cohomology in middle dimension of the Milnor fiber, which is, a free finite generated abelian group, and it carries the monodromy automorphism. Milnor fiber is like the level set of f and epsilon. We take epsilon around the circle, you get the monodromy. So there's a relation between those two, meaning that this is an abelian group, but if you extend it to a complex vector space, then it is actually isomorphic to this one here. And in terms of the algebra, you can obtain, well, not directly the monodromy, but you could put an algebraic connection, whose monodromy is equal to this topological. Okay. What do we know about the monodromy? Well, there's the classical monodromy theorem that says that the monodromy is always quasi-unipotent. So the eigenvalues are roots of unity. So given that we know that, the next question is, what is the size of the Jordan blocks? And the other part of the monodromy theorem is that the size of the Jordan blocks is at most the dimension, the number of variables n. Okay, so I always get confused between n and n plus 1. But if you have a interest on a surface that has a Jordan block of size 2, and it's a function of 2 variables, that gives rise to that. So I think I'm okay. But there's actually a more interesting theorem. So these two things, so the question is, what's the relation between the left side and the right side? And you can say there's a natural relation because there's one way of writing down the D module that gives rise to the Gauss-Mannheim connection, which actually involves multiplication with f. But in spite of that, the relation is actually not obvious. There's a theorem due to Lachenko and Shirk, which gives you a better, it gives you a bound here which says if the kth power of F is in the Jacobian ideal, then all the Jordan blocks of the monodromy are of size less or equal than K. Okay? So in particular, if F itself is in the Jacobian ideal, then the Jordan blocks are of size 1, which means that the monodromy is diagonalized. It's a hence of finite order because the eigenvalue condition. And that's actually true. So because we know from Lee's theorem, if F lies in Jacobian, it is weighted homogeneous, and one of the first examples that were computed is that if you have a weighted homogeneous singularity, then the monodromy is of finite order. It's very straightforward argument. Okay. So just to say, since we know that it's quasi-unipotent, the obvious question is for the monodromy, what is the size of the Jordan blocks? And we have two bounds. One depends only on the dimension. And one depends on this condition here, which power of F lies in the Jacobian ideal. And because of this theorem here, the bound by Lachenko and Shirk is actually strictly stronger than what we get from the monodromy theorem. Okay. Good. In fact, this thing here, this property here, I think was the original motivation for thinking that this one might be true. They ask themselves, maybe this n here is related to the n in the monodromy. Okay, so this will never come back. It's just motivation. But we have this connection with quasi-unipotent monodromy. We ask ourselves what's the size of the Jordan blocks, and there are essentially two bounds. One is just dimension dependent, the other depends on n itself. Now for the actual topic. So I will restrict myself, except maybe for the very end, where I make some very vague remark, to projective to Fano varieties, which means to monotone closed symplectic manifolds for symplectic geometries. So quantum cohomology, well, we take the ordinary complex cohomology of M, we add a Fano variable, quantum variable Q of degree 2 in this case here, and then we have the quantum product, which deforms the classical cup product. So in the sense that if you set Q equals 0, you get the classical cohomology ring. On the other hand, this is maybe not a good idea because the classical cohomology ring is quite complicated. It's almost everything is nilpotent, right? So the other thing is where you set Q equals 1, or maybe if you set Q has degree 2, so if you set Q equals 1, you destroy the grading. So let's say we invert Q, and generally the ring will become simple. Okay? So the thing that I'm particularly interested in, so this is the graded ring. So and here I already inverted Q, as you can see. So there's this element C1 of M is an element of degree 2, first Chern class, Q inverse of that is an element of degree 0. This is the degree 0 endomorphism. So each degree is just an endomorphism of a finite dimensional complex vector space. It has eigenvalues. And of course, well, this one here, this is a commutative ring, so everything commutes with each other. So this decomposes the ring into generalized eigenspaces. Okay. So that's good. Okay. So the other object, so this, you should really think of this as an analog of the previous slide. So there's an object on the left and there's an object on the right, which is related but a priori a little different. So the quantum connection, I add another variable, which was of degree 2. Here I have to apologize. A lot of things in this talk are very rudimentary versions of things in Tony's talk, but my variable t is his variable u. I'm sorry to say that. So t you think of as the generator of H2 of BS1. So you add, but anyway, you add another some sort of S1 equilibrium theory. You add this variable t, and then there's a connection here, which is uses again the quantum product with the first Chern class, and then it also has differentiation d by dq. So d by dq reduces degree by 2, then you multiply dq that increases degree by 2, and then you multiply t again. So this is an operation of degree 2, but it's some kind of connection. Okay. So in a sense, if you set t equals 0, then this derivative term here disappears. To set t equals 0, and you end up with just the quantum product with C1. So in a sense, t equals 0 brings back to quantum cohomology. The other thing which we do is we invert Q as before, but then we t complete. There are various motivations for t completing, but then we just do it to introduce formal power series in T. So on the ordinary quantum cohomology, we have this splitting here, into eigenspaces, the splitting here in a naive way is not compatible with differentiation d by dq. Okay? So, which means in order to, but there's an elementary lemma here, which sort of was also in the background of Tony's talk, done by formal power series and power by power and t, which says that you can split this one here into pieces, one for each eigenvalue, such that the pieces are preserved by this connection, and such that if you set t equals 0, the splitting reduces to this one. And actually, there's a unique way to do it. It's sort of, you can look it up into sort of ODE textbooks from the first half of the 20th century. When they're still doing formal power series in ODE textbooks. So there's the splitting. So, I'm trying to ask myself, what is the nature of this connection? And so now we have the splitting, we can ask ourselves, what is the nature of the connection of each side? Okay?
Similar to what happens.
Oh, good. Can you get a second? Okay. So there's a question about order 2 and so on. Okay. So, maybe you find this way of writing the connection into that's maybe the most natural way to find it kind of disgusting because it's got degree 2 and so on, and it differentiates in a very strange direction. So the first thing we can do is we can divide by q if I have inverted q. So I call it, so this is an object of degree 0. And also I want to change variables from, instead of t and q are both variables of degree 2, which is a pain in the butt. So let me divide out and introduce this variable tau here of degree 0. So the space we're acting now, which is still complete, is this one here. So we have formal power series in tau with coefficients that are Laurent polynomials in q. Let me fix this in a graded space. Let me just look in degree d. And if you look at it, so this, you think of this as differentiation by dq, but you can also, this is exactly the same operation, think of this as an operation that differentiates with respect to tau, and it's this operation, okay? So it differentiates more precisely in the direction of tau squared d tau, and then there's a term, this term that we're used to, and another term which, well, you have to put degree considerations that will come up. So this is the grading operator that multiplies the degree k homology class by k. And this is the degree in which we're operating in degree d. So I've rewritten the connection this way, and well, it's differentiated in this direction, so we can divide by this tau squared, and we get an ordinary tau connection. If you divide here by tau squared, you will see that this connection here has a quadratic pole. Okay? So now in a more normal way, we can say the connection here has a quadratic pole, but we can still split it into pieces according to eigenspaces. So we get a bunch of different connections, each of which has a quadratic pole. And so a recent theorem that's due to Zeon Chen is that this quadratic pole can be reduced to a scalar one, to a multiple of the identity. You can see we have, if you divide that minus tau to the minus 2, you'll get a minus here, which is why you have minus the eigenvalue. So this connection here, each summand of this connection is isomorphic to one where the quadratic pole has a very simple form, it's a multiple of the identity, and the rest has a regular singularity and has a simple pole. Okay? So I should say, if the quantum product with the first term class is diagonalizable, then there's again an elementary proof of this by power by power. It's kind of easy because here you're saying that the quadratic pole order term is a direct sum of multiples of the identity, and it's a semi-simple, that's already the case. So you just have to adjust the higher order terms to follow this. Okay? But the general case is there is no, that I know of, no elementary proof in the sense of just cutting around the bottom house. The other thing which I didn't put in the theorem is that each piece here, so it has a simple pole, regular singularity. By the way, regular singularity means that we can talk about its monodromy even though it's defined over formal power series. It makes sense. But we also know, that's also part of this theorem, that the monodromy is quasi-unipotent. Okay, so now we have each of these summands, we know each has a quadratic pole. The quadratic pole is a very simple form, we can subtract it, and then we get a residual thing which has a quasi-unipotent monodromy, a regular singularity, and we can ask what is this structure of the Jordan blocks. That's the obvious next question. That very good? Okay. Okay. So as before, there are two bounds. One depends only on the dimension, the other doesn't. This bound here is dimension dependent. So the monodromy of these is here Jordan blocks, and there's two slightly different bounds. So if the block is unipotent, which means belongs to the corresponding lambda is 1, then the size is n plus 1, n is the complex dimension of n, excuse me, and otherwise it is n for all groups of unity. This is the only theorem. There's an additional assumption here, which is unfortunately essential for this argument. Algebraic geometry should admit a smooth anticanonical divisor. Anyway, I don't want to discuss it too much, but this is the only theorem in this talk that is not elementary in any way, because the proof is based on the Petrov-Weintraub Vologodsky non-commutative version of the monodromy theorem in a somewhat complicated way. Okay, I always get confused about this n and n plus 1. Am I off by 1? Why is there this difference? Okay, so every time I have to talk about this, I end up completely confused. But I think maybe this one here is helpful. So suppose that M had no rational curves. This is of course impossible for a Fano variety, but in symplectic geometry it could be possible, which means there's no examples, but we don't know how to exclude it. So in that case, the quantum product is just the ordinary cup product. And the quantum connection has a regular singularities at 0 and infinity. Here we're looking at tau equals 0, which is q over t equals infinity. And the monodromy is conjugate to just cup product in the first Chern class. So it has a unipotent block of size n plus 1. So e to the quantum product, e to the cup product of the first Chern class. It has a unipotent product of size n plus 1. So this is this n plus 1 here. What does this actually show, since we don't have any examples? I think this shows that, there is no reasonably easy way that you can improve this to n, because if you manage to improve this to n, you will have proved that every monotone symplectic manifold has a rational curve, since the methods are intrinsically symplectic, and then we will probably get an award and become famous, but I doubt that we will go in this way. Okay? All right, so this is the dimension-dependent bound. Unfortunately, there's this additional assumption. Well, this is unconditional. This is a new theorem, which says the following thing. You look at just this endomorphism, essentially quantum multiplication with the first term, this one here. Okay, so it has eigenvalues, right? And suppose that all the Jordan blocks here are of size for some eigenvalue lambda I, of size less or equal ki. Then the same thing applies to this monodromy of this residual connection. All the Jordan blocks of size less or equal than ki. So this is the analog of the theorem that says, depending on which power of f lies in the Jacobian ideal, it's because the power, in a singularity theory context, multiplication with f is a nilpotent operator, and you're asking for its Jordan blocks, they determine the Jordan blocks of the monodromy. So in this case here, it is the same thing. In particular, in the case where this is diagonalizable, then we have ki equals to 1 for all I, and so the monodromy of this connection here is of finite order. Okay. So now there's one case of this which was already known, which is if the quantum homology is semi-simple. Now here I don't have a lot of parameters. Quantum homology is semi-simple really means with a single parameter q, it decomposes as the sum of one-dimensional things. So if that is true, then the quantum connection was analyzed very exhaustively in Dubrovin's work, and he proved that in that case here the monodromy is indeed on each sum it's plus or minus the identity, depending on the dimension d actually. And so this is much stronger than this one here, but of course the corollary here, the assumptions are somewhat weaker. The generalizability of this one here is much weaker than semi-simplicity, and this theorem is somewhat more general. Okay, so these are the two bounds. They're a little different. Okay, I will say a little bit about the proof. Okay, so this changes context somewhat. So following Zihong Chen's work, all this is done by reduction to characteristic P, by which I would not mean that you take the Fano and you reduce it mod P, but that you simply work with cohomology coefficients in characteristic P. Okay, and the advantage is that a connection in positive characteristic has an additional invariant, which is a linear endomorphism called the P curvature. This is the definition. So you just take the connection and you take its P power, and in this case here, well, because you're differentiating QD by dQ direction, you have to subtract this term here. Or you could take the connection TD by dQ, where you divide it by Q, and then it's just the P power. Anyway, this is the P curvature, it's Q linear endomorphism, and the nature is very, that you can say a lot of things about the conjecture. And so the lemma that makes the previous box theorem here work is this one here. This is a special case of the conjecture of JDEs, if not the best in the mind, which is, you can stop taking pictures. Distracts me like nowhere. Sorry, so this only works in this monotone or Fano case, which is that the P curvature of the quantum connection has a different interpretation in terms of something that's called the quantum Steenrod operation, which is given, it doesn't involve different. So the thing about the P curvature is that when you look at this P power, it looks like an order P differential operator, but in fact, everything cancels out and it's actually an endomorphism with no derivatives. So here on the right-hand side, this quantum Steenrod endomorphism a priori has actually no derivatives. Okay. Now I will talk a little bit more about quantum Steenrod operations later, but roughly speaking, what happens is you take a cohomology class B, which in this case here is the first Chern class, and a Q coefficient, and for each of those you have an endomorphism of well our space with Q plus minus 1 T, and there's a slightly annoying odd variable of degree 1 because the variable T can be thought of as depending on S1 symmetry, but the Steenrod operation, just like the classical Steenrod operation, come from symmetry with respect to a finite group. In this case here, Z mod P, and so this coefficient, these two variables in the coefficient ring come from the this should be a K actually. I'm going to work in a field. Characteristic P field K. I apologize for that. But anyway, this is the cohomology of the coefficient ring of the covariant cohomology, which is why you have this T and theta, but it's not terribly relevant. We see in many cases actually vanishes. So we know that these quantum Steenrod operations are always covariantly constant with respect to the quantum connection, which is nice because the P curvature really commutes with the quantum connection by definition. But more importantly, so they depend on a variable B, but they are compatible with quantum multiplication. So the composition of operations is actually the operation associated to the quantum product. So this means that once we know this lemma here, any relation that C1 of M satisfies will be satisfied by the P curvature. Okay, so we can say in the quantum cohomology ring, what does C1 of M actually satisfy? And the P curvature will satisfy the same. So I wrote this down as a little amusing corollary, which is you take this one here, quantum product with this, take its minimal polynomial, maybe even define it with integers, right? And then if you take that minimal polynomial and you apply it to the P curvature, that actually gives you 0, with FP coefficient, because obviously this Q sigma C1 satisfies F of C1 equals 0, and therefore this one here vanishes, and therefore that one vanishes. So this is a kind of fun to take a very simple example to just have a computer compute this and figure out this is like a sequence of mod P congruences for powers of the quantum connection. Anyway, but this is so the proof that I'm actually not too difficult. This actually involves these two properties and a slightly souped up version of this corollary argument that yields this theorem. I told you there was not going to be a huge amount of stuff. So those are the two bounds. I want to say one more thing, which is kind of obvious, which is in the singularity theory case, we had two bounds, one the dimension, the other one from the Jacobian ideal, but the second one was stronger than the first one. So here we actually don't know this. So if I have the just a quantum product with the first Chern class, and I ask myself, what are the Jordan blocks, right? I don't know that I have the same bound n plus 1 that I have for the monodromy. So maybe if some Fano informed person, hello, can check some examples and tell me that the Jordan blocks of this thing here are not more than the dimension, and in all known cases they're good, or if actually it transgresses that, then I can give up on this. Okay. I should say that the relation between singularity theory and this And this problem is not very firm because the mirrors, the Fano varieties, are not obligated to have isolated singularities.
But doesn't this correspond to the number of components of the biggest single fiber?
Does this not correspond to the number of components of the singular field? Well, it responds to the depth of intersection. Well, I don't know actually. Sorry, there's, I think confusing it for the monodromy, it's kind of obvious, but this is not the monodromy. This is like a non-equivalent case. I shouldn't say anything that I don't understand myself, if that's possible. But not too much.
Has this been tested on those things which have elliptic curve?
Has this, the question was, has this been tested on the things which have, you know, like an elliptic curve as a critical locus? Yeah. Okay. What is the time? Okay, I think I'm good. Are there any questions at this point? We can kind of take a little break. Have some questions. I can go back if there's something you didn't understand. You can say I didn't understand anything. Questions? I can have at least one. You're worse than a calculus class. Okay. Second part of my talk. Slightly different, same thing, but I want to go back to the question of splitting the quantum connection into pieces. Okay. And here the motivation comes from, like, again, homological real symmetry, but really in the more abstract form of and the question I want to ask myself is this. So suppose that in quantum homology, you know, the identity is written as a sum of mutually orthogonal idempotents. Okay? So the quantum connection as a ring, it splits into pieces that are generated by these idempotents. Now, the idea is this: if the quantum cohomology is split, there's a natural map from the quantum cohomology to the Hochschild cohomology of the Fukaya category, here being somewhat ambiguous about what I mean by Fukaya category. And so if you get idempotents in quantum cohomology, you get idempotents in Hochschild cohomology, then you'll split this category into a direct sum of mutually orthogonal categories. And so any other structure that's accessible to homological mirror symmetry should then split correspondingly. Okay? By which I mean what? Well, anything that you can associate with the Fukaya category that has some interpretation. And in particular, the quantum connection. Okay? So you should have from a splitting of quantum cohomology, you should get a splitting of the quantum connection. Now, the first part here was, it's pretty solid, but the second part, to get splitting of the quantum connection, you need to really know that the quantum connection can be recovered from the Fukaya category. There's a map, a comparison map, the open-closed map. If we know that this is an isomorphism, then we're good. But it's hard to show that this is an isomorphism. There are actually a huge amount of cases of Fano varieties where this is actually knowable. Okay, and moreover, every time you prove it, it seems to be done in a sort of different way, some generation criteria producing some geometry at home. So a little bit depressing. So I'll put down, however, the conjecture there, which says, okay, assume that you have a splitting of the identity into idempotents, then there is a splitting of the quantum connection in this T completed version, okay, which when reduced to T equals 0 recovers the splitting of quantum homology given by this idempotents. And the splitting, should be compatible with the connection. So the reason why you want to do T completion is from this motivation here, the quantum connection corresponds to the Getzler-Gauss-Mani connection on the periodic cyclic homology of the Fukaya category, and the periodic cyclic homology very strongly wants you to complete with respect to the S1 parameter. Okay. Okay, so there's obviously one example that we talked about before, which is if these things here are projectors to the generalized eigenspaces of this, okay, then we know that we can get such splitting, in fact, there's a unique such splitting, and it's constructed by elementary reasons. Okay. So, but in generally speaking, there could be two different idempotents that belong to the same eigenspace of quantum multiplication with C1. And then this method here doesn't apply. Okay. So for instance, if you take the n to be CP1 cross CP1, the quantum multiplication with the first Chern class has 3 eigenvalues. So the elementary theorem gives you a splitting into 3 summas, but actually you have splitting into four, given that four line.
Well, I
Yes.
think before the loop, it should only order of total.
It's actually, yeah, so the question was, is it small? Actually, it's very small, because I'm only allowing one variable in H2, which is radial rescaling in the anticanonical class. So yeah, so generically, I cannot use generics. Otherwise, I could say on a generic point, maybe the eigenvalues will be separated. And but you know, the other case is, so if we have this same simplicity in this very strong sense, then as you showed, the existence of a splitting follows from the Robbins work. I mean, generally speaking, there's a bit of a weasel word here, you know. You might think that just arguing order by order in T, you could at least establish the uniqueness of a splitting, but that's not true. Uniqueness and existence are not equally hard. So here we get an elementary existence theorem, which also comes with its uniqueness theorem. And here I use canonical as some sort of weasel word here.
Can we use symplectic topology to get rid of the symplectic topology produce one, or
yeah, well, I'll get to that. Okay, so the question is, can symplectic topology, okay, maybe the weasel word, at least as a symplectic topologist, you would say this should be invariant with respect to the action of symplectic automorphisms. Okay, I think that's a reasonable thing. Or, you know, you might have different ideas about if you have a Lagrangian correspondence or something like that, the generalized symplectic automorphism. So here we have a preferred splitting comes from Dubrovin's work. I'm not really sure that existence, but you know, it gives you a strong feeling that this splitting should be the right one. Nevertheless, you know, this is a promising start, right? These two examples, but I don't actually know an elementary way to get this conjecture. In general, I could be wrong, okay, but at least nothing that I know. You know, probably you shouldn't take me too seriously because, you know, I read Dubrovin's argument uses a little bit of geometry, which is some 5-point WDVD equation, and I read it many times, and it's still like a little miracle to me. So maybe I'm not the best person to say what is or isn't possible. But anyway, so I'm thinking about this conjecture. There is actually a third partial result, which points in a slightly different direction. Okay, which is again, you know, if we take coefficients mod p, so say, my notation is inconsistent. Use coefficients in Fp on the field F of characteristic P, and you have these quantum Steenrod operations. In that case here, remember the quantum Steenrod operations satisfy the same relation as the classes that you put in. So if you put in an idempotent class, you get an idempotent operation. If you put in one, you get the identity. So these things here are projectors that are mutually orthogonal, and they add up to one, and they give you this splitting mod P. So when I defined quantum Steenrod operation, there was this additional variable theta, which was annoying. But in this case here, for an idempotent, actually there's no theta component, so I don't have to apologize. The remarkable thing about these things here is that you don't actually need to have formal completion in T. So if you think in terms of the degree 0 variable tau, which is, you know, a variable in one's function at Fi9, like Fi9 minus 0, then the splitting holds over the entire function Fi9. Okay, now, if this was characteristic 0, this would be absolutely impossible because the monodromy around the opposite end, tau equals infinity, which is q equals 0. I don't know. I mean, I don't think this is possible, but here in this case here, well, it violates Stokes data and all sorts of other things. But in characteristic P, it is possible. Okay, so we cannot actually, you know, we cannot hope for this kind of result in characteristic 0, but there's something which sort of sits in between characteristic 0 and characteristic P, which is a p-adic integers. So from now on, I'll assume that cohomology with coefficients in ZPs or p-adic integers, or you can take the ring of integers in a p-adic number field. Okay. Just don't ask me any questions about rings of integers in p-adic number fields, please, because I don't know anything about them. But okay. Because it's this kind of mixed characteristic thing, I will assume for simplicity that the homology of M is torsion free, or it's at least P torsion free, if you'll excuse me. At least if P is large, that shouldn't be a problem. Okay? And in this case here, you can get a splitting, which is a little better than formal power series, but worse than being polynomial in tau. So when you look at power series whose coefficients are say p-adic integers, there's various convergence properties here. The convergence property that come up here is a slightly wacky one. So you want to look at power series. Say this is the degree 0 variable. I think I look at power series in one variable with coefficients in R, which is the p-adic integers. And I want to ask for the following property. If you take this power series and you reduce it log p to the m, so you reduce all coefficients log p to the m, then you get a polynomial in tau of a specified degree, which is p to the m, p is our prime under consideration, times some constant. And that constant depends on x, but it's the same for all m. So basically, this is the power series. If you reduce it log p to the m, it gets to be a polynomial for every m. And moreover, you have a very mild bound on what the degree of the polynomial is. So now, a standard thing would be to say that these are p-adic power series that converge on the closed unit disk. So convergence on the closed unit disk is equivalent to saying that restriction to p to the m is a polynomial, but without a bound on the degree. I hope I said this right. This is a very slight strengthening of that. If anybody's used to think in terms of p-adic power series and use in polygons, you can ask me afterwards. Okay, but this is great. Okay, and we can use the same strategy to define a version of our usual cohomology here. So this means these are power series in the variable t with coefficients in p-adic q plus minus 1. And if you reduce log p to the m, they become polynomial in t. Now, notice that here, unlike the previous case, t has degree 2, q has degree 2. So if you say, if you had a term in xk that has a very negative degree of q, that puts it in a very negative degree. So it has to be accompanied by a very positive power of t. In other words, for degree reasons, saying that the reduction of Pm does not have high powers of t is the same thing as saying that the reduction of Pm doesn't have too low powers of q, too negative powers of q. Okay, I'll say it again. Okay, so in this case here, maybe we should really look at tau equals t over q. But in this case here, what I'm saying is that the reduction of p to the m gives you a polynomial of t bounded degree, but that's the same thing as saying the reduction of p to the m gives you something in which the pole order terms of q that agree have some sort of bound. Okay, so this is the ring of functions. I'm sorry, I encountered this like a week ago. I don't know what it is. I wrote to Björn Kuhn. He hasn't answered me yet. Anyway, but okay. So this is the theorem. I hope it's correct. It's really fresh out of the oven. Somewhat nervous. So you have this. Now we work with these p-adic integers. We assume that we have the splitting into idempotents in this one here. And then there's a canonical splitting of the quantum connection over this ring here. So it's in particular, you can think of it as a splitting that's convergent on the non-Archimedean closed disk of radius 1 in the variable tau. So you've seen a p-adic convergent splittings before in Tony's talk, but there is for like an elementary power series argument, which says you get some finite radius of convergence. You get radius of convergence 1 and even some kind of tiny improvement. I don't know what to do. But anyway, there's splittings which has the desired property. Sorry, I didn't say that. It's compatible with the quantum. Oh yeah, it's compatible with the quantum connection. When you set t equals 0, it reduces to the splitting of quantum homology given by the EIs. And when you divide by p, you get the previous splitting that I explained. So this is the rule. If you reduce mod p, you end up with polynomials in t by definition. Okay, and you get the previous splitting that is polynomial. Okay, so this gives you a canonical splitting over this in this strange way, which is of course stronger than the original idea of splitting in terms of power series in t, but it requires coefficients in this p-adic integers essentially. Okay, and the proof of this, so this is basically a reflection on the previous use of quantum Steenrod operations. It is so the previous quantum Steenrod operations. Maybe we'll go back. Where did I have it? Right here. So I said you use the quantum Steenrod operation using these idempotents here. And that gives you the projections to the pieces. So now we want to work instead of mod P coefficients, we want to work with P-adic coefficients. So we want to lift these quantum Steenrod operations from characteristic P to P-adics. This unfortunately only works for idempotents, or more precisely, it works for elements of Q sigma D, it works for elements B in cohomology, which with respect to the quantum product have P to the nth roots for all n, but I don't actually know a lot of interesting examples of that, I'm afraid. Here's slightly the most nervous about this because with the idempotents, I'm okay. If anybody manages to construct this for a bunch of other B's, then we get a lot of covariantly constant endomorphisms of the quantum connection. Now in characteristic P, I have no objections, because in characteristic P, there are a ton of functions whose derivative is 0, and correspondingly, you get a huge module of covariantly constant endomorphisms of the quantum connection, which includes all the quantum Steenrod operations. But your ZP has a characteristic 0, so a p-adic, so I'm very nervous. But so far, I seem to be on firm ground that it only works for these ones here. There's these other cases which I don't know enough about to give me a nightmare. Okay, so now I have to finally say a little bit about what quantum Steenrod operations are, right? So as I said, you saw from the coefficient ring involved that quantum Steenrod operations involve the group Z mod P. Okay, and so the lift here depends on a very stupid trick. It's very obvious to use instead Z mod P to the NZ. Okay, so and we use coefficients. We work equivariantly with respect to that, and we use coefficients in the p-adic integers. So if you look at the cohomology of the classic quantum space with these p-adic integers, well, in degree 0, it's of course one-dimensional. In higher, so you get nothing in odd degrees, but in higher even degrees, you get torsion. So mod P to the n torsion here. So if you take n equals 1, that's sort of a disappointment. You say, oh, I'm using ZP as covariance, but I'm now using coefficients characteristic 0, but the cohomology is still P torsion, so you don't really get any new operation. But if you use the higher order cyclic groups, then you get more, because you get more and more torsion. And so these groups sit inside each other, so you can take the union. It's called gamma infinity. Sometimes it's written as Z over P infinity Z. Okay? Even though, there is a remark in Nikolaus Scholze saying you shouldn't say that. So this is now heretical, and I will correspondingly not use it. So this is this. So the cohomology of this infinite discrete group, the gamma infinity, is so the group itself is the direct limit, of course, of these inclusions. The cohomology is the inverse limit of the cohomologies. There's no lim 1 or other things you have to worry about in this context. And so if you take the inverse limit, you actually get the inverse limit of R mod P to the n, and so you get R bracket T. So with this ZP coefficients, this infinite discrete group, which of course sits inside the topological circle group, actually has the same cohomology. So you can use this discrete group as a replacement for the topological circle group, and this is not a new idea by any chance. Okay. I mean, I could say it's, for instance, it appears in Nikolaus and Scholze, but that's like appealing to an entirely different level of complexity here. Anyway, so how does this actually appear here? Well, now finally I have to tell you what quantum Steenrod operations are. So quantum Steenrod operations are a form of genus 0 enumerative geometry. Usually people say it's in a quadratic theory. That's not actually correct because they do not use the stable map for quantification that I know of. Or at least they don't use it in the standard way. But yes, still, that's going to be a technical point. I'll come back to this point in a bit. So, so what you do is you take genus 0 curves with p plus 2 mark points, but they're arranged in a slightly different way. There's a mark point at 0, a mark point at infinity, and then p mark points on the sphere at p's roots of unity. Okay? And then as usual in Gromf-Witten theory, you have to put in cohomology classes or cycles that give constraints at least. So there's two cycles here. Remember the Gromov-Witten, Steenrod goes down. Where are you? There goes an endomorphism, so it has an input and an output, Q sigma B. So the input and output cycles correspond to these 2 points. And at the other points, you put in the same constraint B at each point. Oh, there's one missing here, which is the one we want to Q sigma B. And then the situation is symmetric with respect to the cyclic group of order P. And you do a numerical geometry equidirectly with respect to this symmetry. And usually this is done with what P coefficient, but you can do it with R coefficient, but it's not going to help you because of this one here. That would be n equals 1, so you get still get P torsion. So so what do we do in order? So we want to use the gamma m's. Well, the idea is obvious. You can put P to the m points, here the P to the m points, instead of P points, and you work equivariantly with respect to gamma m, which is the cyclic group of order P to the m. And you get a bunch of higher order operations. And they look like this, the straightforward generalization of the quantum Steenrod operations. Okay. Now we have this cohomology of B gamma m, which is P to the m torsion, so we get more information. In order to lift to P adix, we need to investigate what happens when n gets higher, so that we can form the inverse limit. And this is what happens if n, how we go from m to m minus 1. So here are, here's the quantum Steenrod, sorry, on the, here's the quantum Steenrod operation that's done. So n is the degree of equivariance, corresponds to gamma n, with some class B. So this has the cohomology of the classifying space of gamma n. Now I have the map that's induced by inclusion of groups, so it reduces the symmetry to gamma n minus 1. So after you reduce the symmetry, you again get a quantum Steenrod operation with less symmetry, but not for the same class. Instead of the class B, you apply the Q quantum power, so P full quantum power of the same class. And this is a commutative diagram. And this explains what happens, how the symmetry n is related to the symmetry n minus 1. Now, in the special case where this is an idempotent, of course, the P quantum power of the idempotent is again the idempotent. So in that case, you have EI here and you have EI there, and you just have a commutative diagram here, which reduces n, and you can pass to the inverse limit. Okay? As n gets larger and larger, you get R coefficients, and this is how you get the splitting. Okay, because all these things are compatible with the connection. Now, my last thing I have to do is I have to explain where this diagram comes from, but it's actually proved by picture. It's very simple. Okay, so this is the level n equivariant theory. It has P to the m points. It has the full cyclic symmetry. Now I'm going to reduce the symmetry to one less, which means the only symmetry group, the symmetries that I care about is the one that take one mark point and move it forward by P. Okay, so take one more, there are P to the n mark points, and now the smaller cyclic group moves each forward by P. Which means now I have some freedom to move the points around while preserving the symmetry. What I will do is I will take P subsequent points, I didn't draw this very well, and I will move them closer together. So let's say that above they were like, okay, 4 is not a prime, but they were 25 points, and then I will move them together into 5 groups of 5, that is still Z mod 5 equivalent. And in the limit, I will let each of these groups collide in some way, and that will give you a stable curve and a nodal surface, which has a P, what is in fact a geometry we call bubble components. Each of these bubble components will contain P points. These P points will come in some fixed position, which depends on exactly how they did the degeneration. If you like, you can move them closer together in pairs and get a whole bubble tree. I don't really know. But the fact is, these are not, there's no symmetry on the bubbles. They're really just in fixed position. So if you put B as an input on those P points, then the output cycle is just the P quantum power of B. And so the degeneration here, I've degenerated. I've taken this one here, which is Q sigma and B. I drop the symmetry down, which is this composition here, and I degenerate it in a way that shows that it is the Steenrod operation that's applied to the P quantum power of B. And so this diagram is what you need to go to the inverse limit and construct the desired splittings. Okay, this is kind of stupid. I never claimed that this was particularly intelligent, but not so common to use p-adic integer coefficients meaningfully in symplectic geometry. I mean, it's been tried before in terms of probability theory, what denominators do you have and p-adic conversion, but that's not what we're talking about here. And also maybe the last substantial mathematical point I have to make is, you remember this weird ring with conditions of inverse powers of q or something? So, we apply this to these idempotent EI. EI will have some negative power of q, say, q to the minus 2. So then if you put p of them in, you got q to the minus 2p. If you put p square of them, you got q to the minus 2p squared, and so on. So this condition, this q-adic, this is p-adic convergence condition, it comes directly from this construction here, which is where I made it up. Okay. So this is the way that I think this splittings will be constructed. I had a number of questions now that I got there, some of which may be stupid questions. Okay, so this is a splitting. I started the connection with an irregular singularity, and I produce these splittings. And I would, of course, like to know whether in other situations which give rise to an irregular singularity, already mentioned in Tony's talk, let's say, you have a family over A1, so you have the Gauss-Manning system, which has irregular singularities. You take its Fourier Laplace transform, that will produce an irregular singularity of infinity. And I would like to know whether in this case here, we have similar splittings. So the splittings would correspond to the connected components of the critical locus of the function. So if several lie in the same fiber, there should still be a splitting into pieces. And I would like the splitting to be not just formal, but to actually be p-adic conversion in the same sense, with radius convergence 1 and so on. There are non-commutative geometry analogs of quantum Steenrod operations due to Zihong Chen, but well, let's leave it to the future, what's going on. So that's my honest question here. Second question is, well, I restricted to Fano monotone symplectic manifold. This is like a bad idea because we want to apply it to split the chi-vectors of blow-ups and so on. Okay. But it's because I'm stuck in the 1980s when it comes to defining invariants, and these are invariants that have to be defined with denominators. I've used these invariants integrally, right, without ZP, not QP. Now that there's something called the weakly monotone case, where you can also do this, and I could generalize this quantum Steenrod operation. The problem with that is the weakly monotone case actually falls into 3 subcases, which is monotone, Calabi-Yau, which is pointless because there are no interesting idempotents in the quantum homology of Calabi-Yau for degree reasons, and cases where the first Chern class is divisible by some fairly large number. And so that third case, well, it applies to all varieties of complex dimension 2 or 3, so it's not trivial, but in higher dimensions, it gets more and more cumbersome. And so, for instance, if I don't need weakly monotone and I want to apply to blowups of 4-dimension 2 varieties, then I can only do dimension up to 3, which is disappointing. Now, recently there's been a lot of work on foundations of pseudo-holomorphic curve cases. So there's much better tech. In particular, Bai and Zhu extracted some sort of integer part of the Gromflit invariance in genus 0 in quite high generality. So you can do that, I assume, this is a very general principle, to these quantum Steenrod operations as well. It's not so clear that the resulting things will have the properties that I need. Because the approach there is you start with rational, a priori rational invariants, and you write them as a sum of contributions, one of which is kind of integral, and you focus on that contribution. But hey, it's good. The other option, obviously, it confuses me, but maybe it will not confuse smarter people, is to say, no, what you should do is look at something which I haven't really taken into account, which is the degree of the rational curves. Depending on the degree, the amount of orbital points in the modular space of stable maps, complexity of the orbital symmetry groups is bounded. You will get powers of P inverse, but just keep carefully track of which powers of P inverse you get. That is the other use of p-adic that I mentioned before that's been tried. The reason why I find this slightly confusing is because in my construction, at first I use mod p to the n. And so you have to be careful that when you do mod p to the n and you introduce inverse powers of p, that there are not more than m of them. Otherwise, your thing will not make any sense. But you know, it is a possibility. Just I wouldn't even know how to formulate the statement that I want to. Okay. So this is, but this would be obviously desirable. I don't want to say what it exactly says about the quantum connection, in which sense it splits, because I can't actually prove anything. But it really depends on what the outcome of this will be, whether you believe that the right hand will work, you get a much stronger statement, or that the left hand will work, and you need to think carefully about what the statement is. Okay. Final remark, slightly different direction, right? So I've started with something which was splitting over FP, which we knew how to do, and I lifted it to p-adics. There are other ways to do this, right? So if you, presumably, if you take the Fukaya category with FP coefficients, which has a splitting, it just depends on FP idempotent, and you apply a topological periodic cyclic homology, then that may lift it to characteristic zero, the relations between that and crystalline homology. A little bit, so I've been asked about this. This is an interesting thing from the point of view of symplectic geometry, where maybe the mod p Fukaya category actually gives you characteristic zero information. Is important. But this is really, in order to get this, you really have to do periodic cyclic homology. So the variable t will always be inverted, which is a little bit of a problem for the specific questions I've thought about here, because the question will always find something which is compatible with reduction to t equals 0. And once you've inverted, you can no longer do this reduction. And that is the end of my story. Thank you very much for listening.